Started with the last session here. So you may have noticed that we had kind of a tools, programming languages session. So this session is a little bit more focused on kind of results on some of the latest ARM-based processors. Our first presenter is Eric Lequiniou. I hope I said that correctly. He's the Vice President of the Radioss Development and Altair Solver HPC division. He's an expert in software optimization, parallelization for multi-core architectures and accelerators. And he developed the hybrid MPP parallel version of Altair's Radioss finite element software. I will hand it off to you. Eric, thank you so much for joining us, and we look forward to your talk.
Thank you, Jeff. Thanks for the nice introduction. So I will try to share my screen. Okay, let's stop one. Oh, yes. It seems that I have some problem with the Zoom. Let me check. Yes, I need to add Zoom. Oh, okay. The problem is that I need to restart Zoom if I want to apply the change. So I will try to do that. So I will reconnect. Okay.
Okay, that sounds fine. Apologies, we should have tested knowing that I actually ran into this issue as well. So this is I don't know if this is a new Mac update thing, but there's some new permissions that it seems like Zoom is requesting.
Okay. So let's try now. Okay, sounds that it's better. Okay.
Great.
So, do you see my screen? Yeah. Okay. So sorry for the small overhead. I'm not an expert of, let's say, of Zoom. So yeah. Okay. So is it okay for everyone? Do you see my screen? Yeah.
Yes, that looks great.
Yeah. Okay. Okay. Great. So yeah. So yeah, I started in fact in a Radioss team 27 years ago. Yeah, I know quite well Radioss, and I ported on different platform machine in my, let's say, developer life previously. And today I give you a talk about the progress and the latest achievement we have made porting Altair Radioss on ARM processors. I am really happy to be here, at least virtually. It's I think my fourth ARM user group, so it's always a pleasure to be here and to see the progress from year to year. So I will do the same concerning my company and my application. Altair vision is to transform enterprise decision-making by leveraging the convergence of simulation, high-performance computing, and artificial intelligence. And in fact, in Altair, we have a broad portfolio of solutions in data analytics and AI. In physics simulation, we will see one example rapidly. In design modeling and visualization, in Internet of Things, in high-performance computing on cloud computing with the PBS professional suite. And all those applications we develop in-house, but also we have a partnership with other software vendors through the Altair Partner Alliance. And all those applications, whether they are in-house or third-party, our customers can access them through a unique license. So it maximizes the return of investment of our customers. So today I will talk about Radioss, which is our solution for crash simulation. Indeed, Radioss is used in the industry for crashworthiness since more than 30 years. And now it is used also on other verticals like electronics, consumer goods. It is also used heavily in defense. In fact, for crash, it has, let's say, many physics inside. So because crash simulation are quite complex, so inside you want to model, for example, the deployment of the different airbags, and those airbags are different physics. So we have, let's say, very precise formulation to handle that. We need to look at a very high nonlinear phenomenon that occur during the crash, which is high-speed deformation. So we need to take into account failure of materials. So it's really important, especially in the context of reduction of CO2 emission, in the context of EV vehicles with, let's say, new type of aluminum parts, something like that, with the battery cells, something which are quite complex. So we really need to follow that, as well as also the, let's say, the evolution of regulation. So we provide also sets of dummies, barriers, and to look at the safety of the car. A lot of simulation also embed fluid structure interaction. So for example, during a rollover, if you want to look at what happens in the fuel tank, so it's important. And one common point with all those simulations, they are really compute intensive. So we always put attention to computing power, to new platforms, and also to optimize our code for new platforms, and to put a focus on parallelization, of course. So in terms of parallelization, our code is based on a hybrid version, so domain decomposition and MPI message passing, and second level of parallelism with OpenMP parallelization. And indeed, we have a third level of parallelization, which is vectorization. In fact, Radioss at the beginning was, let's say, designed to be very efficient on, let's say, a vector supercomputer. So it's good to see that technologies that were at the inception of Radioss today are revival. With, let's say, AVX 512 and SVE. So we see that more and more we need also to have very well vectorized code. It's important to maximize performance. One point is that on ARM, the MPI library that we use is OpenMPI. And also in working with industry customer, it's very important to pay attention of repeatability and robustness. So unique feature of Radioss is whatever number of MPI, OpenMP threads used, we warranty a unique numerical result. So this is a special option that is inside the code, and which is very important, for example, to be able to reproduce problems on a given machine. By default, it's double precision because of the type of problems which are really non-linear. But we do have also a single precision, which allow more performance. So just to illustrate the level of scalability of performance that we achieve with this code, I put on the right this scalability curve that I presented at SC19 ARM user group. And indeed, this is a comparison of performance scalability that we obtain on ARM. Here it was on the Bristol cluster, so with Thunder X2 CPU, and we see that the scalability is very good. The cluster was equipped, if I remember well, with the InfiniBand high-speed interconnect. And indeed, compared to the reference, we were even better. Okay, so it's really the key point is how to improve and to keep this scalability over nodes when we also maximize the single node performance. For this porting on ARM, we based this porting with a strong partnership with ARM. It's very important because Radioss it's a Fortran, mainly Fortran code with several millions line of code. So it's a good example to assess a compiler. But you know, even the best compiler tool, you always face some issues. And yes, so the fact to have a reactive team to help us was key in this porting. So, for example, I talked previously about this option to allow parallel arithmetic producibility. And indeed, at the beginning of the porting, this was not achieved on ARM. So we were able to address this issue and to have the help from the ARM team and their compiler experts in order to address the issue and to give us recommendation in order to keep this functionality working on ARM, which was greatly appreciated. Also, today I will focus the performance on the Ampere Ultra machine results that we obtain thanks to the help of ARM team. Indeed, we use tools from ARM, not only on ARM, but also on x86. And for instance, the DDT parallel debugger is our preferred parallel debugger for the Radioss development team. During this porting, we also collaborated with all other partners interacting in this ecosystem. So Marvel, and thanks to them, we got our first ARM-based system that we continue to use to build our code and to run our in-house QA. With HPE, with their facilities in Grenoble, in France, close to the Radioss development team, which is based in south of France, in Sofia, with also some offices in Grenoble, so efficient to collaborate with them. And also who provided the access to the Bristol University for the studies that we made on the cluster. Also with Fujitsu and Riken to assess also the code on the A64FX, which is the first SVE capable code, so interesting in terms of vectorization. And also on the cloud with AWS, testing the Graviton 2 more recently. So to summarize the different porting steps, I tried to illustrate that, taking the example of the Torus 10 million element benchmark. So it's a front car crash. 10 million of elements, it's something which is, let's say, nowadays common in the industry. This represents something that will take around a night to run on a cluster processor. And this is typically how the automobile OEM works. That is to be able to look at the preparation of the simulation during the day, to consult and to look at the result from previous experiments, and to run new iterations during the night. So it's important to be able to have a good performance, to continue to be able to run overnight, even if the size of models continue to increase, because the complexity, I talked about e-vehicle, for example, the battery packs is already a big part that comes in addition to the rest of the car. So this benchmark benchmark here, it's only the first 2 milliseconds that we run on a single node. So I put single node results. So the porting started in 2018, and at SC18 at the ARM user group, I was able to show the first result. It was a proof of concept, and we showed that the performance was correct with Marvel Thunder X2. And 1 year later, at SC19, it was, let's say, a moderate improvement, but the focus was more on the scalability tests that we were not able to address at the first year. So this is the present result of the scalability that I presented in the slide just earlier. And then in 2020, we continue to test other hardware, so the A64FX. And the end of 2020, we tested Radioss on the cloud on ARM with the Graviton 2. So it's 64 cores, so comparable to the Marvel, but here it's a single socket. And on the Graviton 2, we saw some good improvement with something like 20% improvement in the elapsed time. So here, smaller is better, of course. So this was interesting, and so we decided in the beginning of 2021 to first release Radioss on ARM platform. So this was the first release of commercial release of Radioss, which is now available on ARM. And later on in 2021, so in fact, few weeks before this conference, with the help of our ARM team, we were able to test a new platform, which is the Ampere Ultra. And it's very interesting because here in single node, we see that the performance increased by more than a factor of 2. And to the 2, I think, compared to the previous results on the Graviton 2. And basically, we see that the scalability continues with the number of cores that we have on a single node. So here, 160 cores instead of 64 cores in the previous case. So this is the results that I will detail. So in fact, this Ampere Ultra is based on Neoverse N1 platform, so like the Graviton 2. But the game changer is that it embeds more cores, so 80 cores per socket, so with dual socket node up to 160 cores. So for the moment, we tested only single node. So we did some scalability tests inside the node, and we see that going from 20 cores to 40 cores, 80 cores, and up to 160 cores, the full node, we see a good scalability. So one detail is that code like Radioss are explicit code, and generally they are compute intensive, but also memory bound because they keep, let's say, doing the kind of vector operations that they need to relaunch in memory. So the balance between the compute and the memory is key. And here what we see is that we can continue to have a good efficiency while we increase the number of cores on the machine. So something like 70% internal efficiency, which is good. We did some other tests. So as I said, Radioss is hybrid code. Generally, on single node, the best performance is achieved running pure MPI. So this is what we see here. So the fastest result for the 2 milliseconds of the Taurus benchmark is obtained with 160 MPI. But we see that if we change the setup and we run more thread on less MPI per node, we maintain very good performance. And in fact, the degradation of performance on single node is less than 3%. And this is something interesting because in fact, what we want to do is to run on more than one node. So the fact that we are as efficient in hybrid than in pure MPI, this means that we can take advantage to reduce the number of MPI per node, so to reduce the overall communication when we will run in multi-node. So this is something that I hope we can test soon to see that we keep a very good scalability on multi-node and keep very good result on this platform. So the takeaway and summary of this presentation, I have emphasized the strong partnership between ARM and Altair. It's important in terms of tools, in terms of support. The continuous improvement in terms of performance that we see since the first POC, and I think this is really what is important, that we see that from generation to generation, the ARM platform deliver better and better performance. So it's very important because in the CAE and crash market, the performance is still very key in the success due to the fact that those type of applications are really compute intensive. The other point is that Radioss is commercially available on ARM-based processor since the release of Altair Simulation 2021. And this is important because this is also something that we need to help to spread the usage of ARM to have more and more commercial application available. And we have seen the very good performance levels that we keep on this Ampere Ultra compared to previous generation of ARM processor. So this becomes a very interesting platform to run simulation, whether it is crash or consumer goods or fleet structure interaction with Radioss. To finish, I really want to thank the ARM team for their help and for this opportunity to be with you virtually today. So really hope that next year I will be able to come back and to meet you in person with some additional results. So thanks a lot for your attention.
Okay, thank you very much. Are there any questions for Eric? I'll start us off with one. I guess I was wondering, so you made this kind of dramatic improvement, over the past 2 or 3 years, using, obviously working closely with ARM and using some of these tools like MAP and DDT. For your application, did you, I think, seeing some of the earlier talks, people spend a lot of time thinking about like vectorization strategies and loop unrolling and things like that. Can you speak to, are there any optimizations that you felt like were really critical to getting good performance on, say, on the latest Neoverse platforms?
Yes, so it's true that it's a key point, and in fact we were proactive. So I explained that Radioss was designed a long time ago, but with the scope to run very fast on supercomputer, vector supercomputer. You remember the Cray and the Fujitsu and others, okay? So in fact, we decided in the development team to keep the vectorization as a strong argument of the code. So we maintain the vectorization and we keep, let's say, some strong rules in the way we develop the application to try to minimize, let's say, complex scheme inside the loop and to keep really comprehensive loop for the compiler. But it's true that the vectorization of 30 years ago and now it's not the same. And indeed, we put a new big effort in vectorization 3-4 years ago, when first I realized that let's say on competitor side, we saw that the size of vectorization increased, and also having in mind the fact that on ARM also the vectorization will be more and more important. So that's the reason why we try to improve a lot the vectorization, even before we started this porting. So I mean that I think that we discovered, let's say, really few problems. So and each time we found problems, we were able to identify them and to have the support from the ARM team in order to find a solution. So what I remember, for example, was the usage of, let's say, of vector versions of the math functions. Because otherwise some loops were not vectorized anymore, because we had, let's say, a sequential, serial version of the square or cosinus or whatever mathematical function. So this was something that was not present at the first version of Radioss, and that from time to time we had the solution and we were able to keep the vectorization with that. So this is the typically kind of problems that we saw in many places in the code, and with the help of ARM compiler team, the support them, we were able to fix. Okay, so it things like that. But I mean, in practice, we didn't have too many places. But I think this is also one, let's say, strong point of Fortran, because at the first presentation today, we saw, let's say, problems on how to improve the code, but it was more on C++ code, which is maybe also something more complex, because I was a little bit surprised to see in this presentation the fact that the Fujitsu compiler was not so great for this code. I think that going to Fortran code, the comparison would be maybe more in favor of the Fujitsu compiler, because of all the historical, let's say, knowledge in the compiler about Fortran code vectorization. I mean, I would be pleased to see others commenting on that, but I think yes, it depends really on the language and the state of vectorization of the code. Sorry, it was a long answer to a short question, but I think it's a key point for a modern application.
Yeah, no, that's great. And I think we had our we had a Embracing ARM workshop in August, and we had some discussion of the Fortran compiler for the Fujitsu branch, and I think kind of varied results for different applications, specifically for Fortran type applications. Okay, well, great. Thank you. That was an excellent answer. Are there any other questions for Eric? Okay, I guess everybody is ready to pick up Radioss and use it.
Yeah, so anyway, if you have a further question, do not hesitate to contact me by email. My email is lequiniou@altair.com. I am on LinkedIn also, so happy to answer to your questions later on also. Okay, thanks a lot. Thanks, Jeff.
Okay, thank you. All right.